Okay, this is the Chapter 2 quiz, Part A. We broke it into two parts. This first part was on potentials and uh, potential differences, potential energy. All right, I have a positive particle that is released at point A, so it is at a position of x equal A, and the potential is shown by this graph. So if I were to increase in my x position, my potential would increase. If I were to decrease my x position, my potential would decrease. So as I move to the right, V goes up. As I move to the left, V goes down. And I want to ask myself, well, what direction is it going to go? I always forget the rule. Remember, we gave the rule that positive and negative particles move from either higher to low potential or what have you. I always like to remember this. If I have two metal plates set up like this is my high potential side, and this is my low potential side. And remember, my electric field inside of here goes in that direction. If I have a positive particle in there, it's going to move in this direction. If I have a negative particle, it's going to move in that direction. So positive particles move from high to low potential. So if I have a positive particle here released at x equal A, then it's going to move from high to low potential. So my positive particle is going to move to the left. That's A. What will a negative particle do? Okay, well, a negative particle will move from low to high potential. And imagine a negative particle released between these two plates. It's going to move from low potential to high potential. So it's seeking higher ground. So it's going to move up the potential. So it's going to move to the left. To the right, excuse me. So to the right. However, there's another correct answer here, and that is that as it moves to the right, when it comes up here, look, it can't move from low to high potential anymore because there is no more high potential, and so it's going to sort of overshoot until it gets over a little ways, and then it's going to start coming back up. And so the negative particle will do this sort of interesting thing where it's going to oscillate back and forth. It'll oscillate back and forth. At a very prescribed rate, actually. You can set it to be very accurate in that way, to oscillate. So you can either put to the right, which is true right at first, but as it goes up over that hump in the potential, it's going to begin oscillating back and forth. It's like like a marble rolling around in a bowl. It's very similar to that. That your energy, very similar, just a marble rolling around in a ball. Which of these treatment statements is true at point P, which is at the center of the square? All right, well, first I'm asking about the electric field and the potential. Now notice that there are equal numbers of negative and positive particles, and I'm at an equidistant from all four. So that tells me right off that my potential is zero, because they're all going to cancel one another out. Remember, potential is a scalar quantity. Now, I also want to consider my electric field. So let's take this particle. My electric field due to that particle is in this direction. My electric field due to this particle is in this direction. My electric field due to this particle is in this direction. And my electric field due to this particle is in this direction. What I've asked myself is, what if I placed a positive particle there? What would be the direction of the force that the particle feels due to each of those charges? And the answer to that will be the direction of the electric field due to each of those charges. Now, these electric fields are all opposite one another and equal in magnitude, so the electric field will also equal zero. So here I have A is the right answer. Now there are different configurations you can have that will give you either zero or non-zero potentials or electric fields, and you'll see some of those in the concept test. All right, two charges are arranged. What is the potential at the top where the smiley face sits? So I want to know what is the potential here. I know that Q is equal to 2 microcoulombs, so this charge is 4 microcoulombs, and this one's minus 8 microcoulombs. To find the potential, I just add up the potentials of all the different charges. All right, so nothing fancy. I'm just adding up these scalar quantities. And remember, potential is KQ over R, so this is going to be K, which is 9 times 10 to the 9th. Q, I'll do this one first, 4 coulombs divided by this distance, which is 1 meter, plus K, it's 9 times 10 to the 9th, Q, this charge, which is minus 8 times 10 to the minus 6 coulombs, divided by 1 meter. Notice that I kept the sign here. Now, normally when we're dealing with electric fields and electric forces, we don't keep the signs in the charges because the signs are accounted for when we determine the direction of the vectors. That's not the case here because these aren't vector quantities. We will need to consider the sign of the charge. So I have included it there when I'm calculating the potential. And let's see, what's this? 36 times 10 to the third. That's 36,000 minus 72,000. So that's minus 36,000 volts. That's A is the right answer. All right, how much work is required to assemble the charges into this configuration if Q is equal to 1 coulomb? Okay, so for each of these, I'm just going to bring a charge into place, and I'm going to remind you that the work is equal to Q times the change in potential. And you want to bring each charge into place and ask yourself how much work was done. So I'm going to first bring this charge plus Q, and I'm going to place it there. Now I'm imagining that there are no other charges, so it doesn't require any force to move a charge around where there are no other charges. So my work here is equal to 0 because my change in potential is equal to 0. Now I'm going to imagine that I'm bringing this plus 2Q charge over here. That's a plus 2 coulomb charge. This was a 1 coulomb charge up here. I'm bringing this plus 2 coulomb charge, and I'm placing it 2 meters from that charge. And now I want to find the work here. So my work is going to equal Q times delta V. That's going to be 2 coulombs times the potential due to that 1 coulomb charge. So that's going to be 9 times 10 to the 9th, K, times Q, 1 coulomb, divided by R, which is 2. Notice what I've done here. This is my charge 2 coulombs that I'm bringing into place. But over here on the delta V, the change in potential for that Q, that 2 coulomb charge, is due to the other charges. So when I consider the charge here, I take into account the other charge. Okay, this is a little more complicated. I'm bringing the 4 coulomb charge into place over here. Now, in this case, I have 2 charges that are causing a change in potential. So I'm going to calculate this work down here. Work is equal to Q times delta V. That was a 4 coulomb charge that I'm bringing into place. And then the delta V is going to be the sum of the potentials due to the other 2 charges. So that is going to be K times 2 coulombs divided by this distance, which is 2 meters. All right, so notice that is the potential due to this charge, plus K times 1 coulomb divided by 2 meters. All right, let's see, my 2's cancel there. I get 4K plus 2K, I get 6K. 6 is 54 times 10 to the 9th joules. Now I want to add up all the work. So I take this work, the work required to bring in that 3rd charge, add it to this value, the work required to bring in the 2nd charge. Well, let's see, I'm sorry, what was it doing? Oh, so now I want to add up the 2 work. So I take this work, which is the work required to bring in that 2nd charge, this work, the work required to bring in the 3rd charge, and then of course this work, the work required to bring in the 1st charge, and add all 3 of those up. See, 9 times 10 to the 9th is 54 times 10 to the 9th. That's going to be A, 6.3 times 10 to the 10th. So just adding up all those works. This is important because when you have collections of charges, they contain a certain amount of energy. And you want to be able to determine what amount of energy those charges contain. Honestly, it probably doesn't have a whole lot of practical applications for most of you. But and sometimes when you use certain instruments, this becomes important. So there you go. But it's kind of interesting that you can have this collection of charges and it actually contains energy. And if you were to let those charges go, they would distribute that energy in some way. All right. This figure shows a positive charge with concentric circles surrounding it. At what points is the potential at its greatest value? All right, well, remember potential is KQ over R. So if R is down, if R goes down, V goes up. So the one with the largest potential are the ones with the smallest radii. That's point C and D. Also notice that point C and D are on an equal potential line. That means they have the same potential. All right. Proton and electron are a constant electric field created by oppositely charged plates. You release a proton, an electron from the negative side. Which feels the larger electric force? All right, well, our electric force is given by F equals QE. They're sitting inside of an electric field. The electric field is the same. The charge is the same. So the force is going to be the same. They're going to feel the same magnitude force, but opposite directions. So the negative particle feel force in that direction, the positive particle feel force in that direction, but of equal magnitude. Proton and electron are in a constant electric field. You release proton, electron from the negative side, which has the larger acceleration. They feel the same force, so the electron, which is smaller, feels the larger acceleration. Similar to a question we had before. Which one has more kinetic energy? All right. The work done by that electric field is equal to Q times delta V, the change in potential. They experience the same change in potential. Likewise, they have the same magnitude of charge. Okay, that means that the work done by the electric field is going to be the same. So they're going to have the same amount of kinetic energy because they're going across the same potential difference. They have the same charge or the same magnitude charge, so they have the same work, and so they both acquire the same kinetic energy. So let's see, what group of charges took more work to bring together from an initial distance apart? Okay, this is like what we did before. So imagine, we're just going to go through these again. Imagine I'm assembling this group of charges. I bring in the +2 charge, and the work required to bring it into place is 0. And then I bring in the +1 charge, and the work required to bring it into place is Q delta V. That's going to be +1 times K times 2 over D. So the total work for that configuration is 0 plus that, which is, what's that, 2K over D. Now let's look at this scenario over here. To bring in the +1 charge at the top, 0 work to bring it in. To bring in the +1 charge over here is going to be Q delta V. That's +1, which is my charge. That's this charge times delta V, which is going to be K +1 over D. But notice this charge is now referring to this one because I'm concerned with the potential due to that topmost charge. And now let's bring in the third charge. Also, let's see, this was equal to then K over D. Now let's bring in this third charge, and it's going to be Q delta V, like we had before. That's going to be +1 times the potential due to these two charges. All right, so that's going to be K times 1 over D plus K times 1 over D. That's the potential due to those two charges. And that's going to be, what, 2K over D. So the total charge here, or the total work rather, is 3K over D. Notice I had 2K over D over here. So this second sorry about that, but this second configuration of charges has more energy. Hold on. I'll get more energy wrapped up in that collection of charges, 3K over D versus the 2K over D in just those two charges. So the positions and the number of charges is very important. I mean, you see here that I had 3 coulombs total of charge, but the way they're configured and the way they're configured is very important in determining the amount of energy that they contain. All right, what is the electric potential at point A? All right, at point A, I have a plus 50 over here and a minus 50 over here. Well, it is closer to the plus 50, so the potential is going to be dominated by that positive charge. Remember, potential is KQ over R. And if R is small, that means V is big. And since R is small for the positive charge, it means that that positive charge is going to dominate the potential. What is it at point B? Well, notice here I'm equidistant from a positive and a negative charge. So the potential here is going to equal 0. Right? I can just calculate this out, right? We can say V is equal to KQ over R plus KQ over R. I'm not going to put in the numbers here, but notice that R is the same for both. On one of them, Q is positive, on the other, Q is negative, so they cancel out. 4-point charges arranged at the corners of the square. Find the electric field and potential at the center of the square. Well, this is similar to what we had before. Since there are equal numbers of positive and negative charges, V is equal to 0. All right, the potential due to this one cancels with that one, and on and on. Now let's look at the electric field. Let's consider this charge. The electric field at this point is in this direction. So if I had a positive particle here, it would travel in this direction or feel a force in that direction. Due to this charge is in that direction. Due to this charge is in that direction. If I had a positive particle there, it would feel a force in that direction. And then, let's see what's going on. Due to this charge in that direction. So here the electric field is not 0, and the potential is 0. So the answer is D. At what point does V equal 0? All right, well here at this point, I'm equidistant from a positive and a negative charge of equal magnitude, and so the potential is going to equal 0 there. But notice that's true also for these other situations, that at every point I'm equidistant from those oppositely charged charges. So the answer is E, all of them. Which of these configuration gives V equals 0 at all points on the x-axis? So this is the x-axis. I want to do a similar thing. Now let's imagine that I'm right here. All right. The potential due to this charge will cancel with the potential due to that charge. Similarly, the potential due to that charge will cancel with potential due to that charge. Because at that point, I'm equidistant from the +1 and the -1 microcoulomb charge. And so their potentials cancel out. Similarly, I'm equidistant from the +2 and the -2. Now, let's consider over here. Let's say that I'm at a point right there. I'm a certain distance from that charge, but I'm a bigger distance from the negative charge. So the potential there does not equal 0 because they don't cancel out, because they're different distances from these oppositely charged objects. Similarly, distance there and distance there. Now, it should be noted that there is a place on this one where the potential equals 0. That equidistant here, those two, the potentials cancel, and those two, the potentials cancel, but not at all points on the x-axis. And let's try this one. This is similar. Those are different distances, so they don't cancel. Different distances, so the potentials don't cancel. So the answer is A is the right answer. Gives V equals 0 on the x-axis. There's some more of these. How about on the y-axis? So now we're looking at the y-axis. Let's see. At a point here, look, those are different distances, so those potentials do not cancel out, so it's not A. Let's take a point there. But those are different distances, similarly with the 1 microcoulombs, so it's not B. How about here? Look, that point is equidistant from the + and -2 microcoulombs. So the answer is C for this one. Which 2 points have the same potential? Well, we're looking for equal potential lines. That's an equal potential line, E and C. So D is the right answer. Which requires the most work to move a positive charge from P to points 1, 2, 3, or 4? All right, I'm moving a positive charge. I'm looking for the most work. Now remember that work is equal to force times displacement. So in order to get the most, to determine which requires the most work, I'm going to want to find one where the force and the displacement are in the same direction. And the force on my positive charge the force due to the electric field will be in this direction. All right. So that's the force due to the electric field. But I'm asking something different. I'm asking which requires the most work to move a positive charge, not for which charge does the electric field do the most work. So it's most difficult to move a charge in this direction because I'm directly opposed to the electric field force. All right. So my displacement and my force in that direction will give me the most work. So moving from P to 1 requires the most work. Notice that, well, let's see, I think that comes up next. Yeah, which requires 0 work. So requires 0 work means moving along path 3 from P to point 3. The reason it requires 0 work, I don't remember if you recall, but work wasn't just force times displacement, but it was FD cosine theta, the angle between F and D. And in this case, that angle theta is 90 degrees, and the cosine of 90 degrees is 0, so that work would equal 0.